Okay, calculus, let's finish the last section of chapter 13, the grand poobah of them all, Lagrange multipliers. So if you recall back to Cal 1, your favorite kind of problems were optimization problems, where you had to find like the maximum volume of a box. Well, now we can do this in multiple dimensions, so let's get to it. Sometimes you have to maximize or minimize a function, but they also give you a constraint that you can work with. It's like trying to build a pen for animals, but you have only a certain amount of fence. Here, it's going to be a little more theoretical. You're going to be maximizing one function or minimizing one function in relation to another function. So consider finding the rectangle of maximum area inscribed inside of an ellipse. Here's an ellipse, and the rectangle is going to be of length x and negative x, so the distance between x and negative x, which is 2x, by the length of y to negative y, which is 2y. So then you'd have a function for the area of the rectangle, and you have a function for the ellipse, and you can work both of them together. So there's one way to visualize what's happening here is the level curves of f represent a family of hyperbolas. In this family, the level curves that meet the constraint correspond to the hyperbolas that intersect the ellipse. And to maximize f of xy, you want to find the hyperbola that just barely satisfies the constraint, the first one that reaches that point. But we're not going to do it that way, it's just a visualization. To find the appropriate hyperbola, though, you would use the fact that two curves are tangent at a point if their gradients are parallel. This means that delta f and delta g, the two functions, must be a scalar multiple of each other in order to have the same parallel slope. Now, in the context of constraint optimization problems, this scalar is denoted by lambda. Lambda is called the Lagrange multiplier, and we'll see how this works in an actual problem. So let's first talk about Lagrange's theorem. Let f and g have continuous first partial derivatives such that f has an extremum point at an xy point. On the smooth constant constraint curve, g of f xy equals c. If delta g is not equal to 0, then there is a real number lambda such that delta f of x equals lambda times the delta g of x. All they're saying really is that if two numbers are not 0, you can always multiply one by some constant to get the other. Furthermore, they're saying the entire gradient is able to be multiplied, and it should meet all the criterion for the second gradient, because that's the idea behind parallel. If you multiply by a number to get x to match, you should also be getting g or y and possibly z in 3 dimensions to match as well. So how are we going to do this? The method of Lagrange multipliers: let f and g satisfy the hypothesis of Lagrange's theorem, and let f have a minimum or maximum subject to the constraint g of xy equals c. To find the minimum or maximum of f, use the following steps. First, simultaneously solve the equations delta f of xy equals lambda delta g of xy and g of xy equals c. So you should end up with a system of equations with at least, in 2 variables, it should be at least a 3 equation systems of equations. If you're doing it in more variables, you could have more systems of equations. And then evaluate f at each solution point to obtain in the first step. The greatest value yields the maximum, and the least value yields the minimum. Now, the hard part about this is working the system. So that's the first thing we're going to do, and we'll talk about how to set it up. So we need to take partials with respect to each of them and set each component partial equal to each other with a lambda multiplier attached to the constraint function. So find the maximum value of f of xy equals 4xy, subject to the constraints that both x and y must be positive, and x squared over 9 plus y squared over 16 equals 1. So one thing we know, let's do the partials for both of these. F of x equals 4y f of y equals 4x. G of x, the derivative of my constraint function, is 2x over 9. G of y equals 2y over 16, which is y over 8. Now it says what you're supposed to do is take your f of x, set it equal to your g of x with a lambda multiplied in. So lambda is a constant multiplied in. And then the second one, 4x, is equal to that same lambda now times g of y. It says your third equation should be something you can use your constraint function. So that would be, if we need to, x squared over 9 plus y squared over 16 equals 1. If you need a third equation, you can use it. Here we only have two variables, so we should be able to solve this using substitution. I'm going to solve the second one for y. Multiply the 8 lambda to the other side, so that means y equals 32, I guess, x divided by lambda. And substitute it in for my y over here. So 4 times 32x over lambda equals lambda times 2x over 9. That means 128x over lambda equals lambda times 2x over 9. So what happened here? Well, we'll multiply lambda over 128x times 9 over 2x equals lambda squared. The x's will cancel, so you get 64 times 9 equals lambda squared. So if I take the square root of both sides, this should be 8 times 3 equals lambda, which means lambda is 24. And I only took the positive one because x has to be positive each time, so I'm not worried about it. Lambda can't be a negative multiplier because that would imply their opposite signs here. So if lambda is 24, what does that mean? Well, we can substitute it back in. So we get 4x, bring this down here, equals 24 times y over 8. So 4x equals 3y. So that means 4/3 x equals y. This is something that we can actually use for substitution in our third equation. So we have x squared over 9 plus 4/3 x over squared over 16 equals 1. That means x squared over 9 plus, this ends up being x squared over 9 equals 1. So that means x squared, multiply both sides by 9, 2x squared equals 9. So x squared equals 9 halves. So x is 3 over the square root of 2. And we know it has to be the positive and not the negative because it says they're positive. Now y is 4/3 times that. So that means y is 4 over the square root of 2. So we get y equals 4 over the square root of 2. But those are our x and y values, and it wants the maximum of this function. So f of xy equals 4 times the square root of 3 over 2 times the square root of 4 over 2. Oh, that's wrong. It's 3 over the square root of 2 and 4 over the square root of 2. I can't copy. Okay. That becomes 4, 12, 48 over 2, which is 24, is the maximum value. And we'll continue with more problems in the next videos. All the whole notes are posted online, but we're just going to do this one and then 3 and 5 as examples.